Hello, I am Marcos Lupion and I will present the work entitled Parallel Input Pipeline for Dynamic Data Augmentation in Deep Learning. My colleagues are Antonio de Toro Castro, Juan Francisco San Juan, Vicente González Ruiz, and Pilar Martínez Ortigosa from the University of Almería. This is the outline that we are going to follow during the presentation. First of all, we are going to give a little introduction to the topic, then we are going to describe the architecture and methodology, and finally the results and conclusions. Well, in the introduction, we want to remark that currently there is a data bottleneck in modern deep learning architecture. The deep learning modules are trained on massive structured datasets, and the process of generating this dataset can be very costly and mainly CPU bounding. For example, if we are dealing with human pose images that must represent the key points of a person, we have the key points in CSV format, and these key points has to be represented in an image. Also, in some cases, the data augmentation process is necessary. Multiplying by 5 or by 10 the size that is required to store this data set, for example, in a HPC cluster. So some environments have very high strict these quotas that may not handle this size or this disk required to store the data augmented dataset. So also in some cases, when the GPUs are being used to train the models, the CPUs may be underutilized. So this is a bottleneck that we are aiming to solve in this work. Also, the frameworks like TensorFlow, PyTorch, or NVIDIA DALI may have several limitations that may constrain the training of the model on this. For example, in TensorFlow, the function defined in the tf.data are limited to a standard format like image and label pairs, and these data are restrict to the functions that are defined by the framework. For example, as we can see in the bottom part of the slide, we can see a neural network that is also performing some data augmentation. The data augmentation, for example, resize and rescale, or data augmentation is embedded into the model. But what happens if we are not dealing with images but with raw data or some other data that do not fit with the framework? There is a problem with the frameworks that do not support complex structured data, for example, with some semantic constraints. In this work, we are dealing with the problem of sign language recognition, which is translated sign language into text. Mainly, we are using here the post-based videos, which do not show the original image, but we are using the landmarks, the key points of the person. So since in these datasets there are different signers that are recording the signs, it's difficult to generalize due to the difference in the feature of the different people that are recording the data. And also in this problem, the data augmentation is key to generalize. So in our proposal, we have developed, or we propose, a new dynamic data loading in TensorFlow. Since with the default functions, we can only store the data in memory, but with the input pipeline customized that we are proposing here, we can dynamic load the data using CPU while the GPU is training the model. Also, in order to have this in real time, the parallelization of the input pipeline is performed using the library multiprocessing from Python. So this is parallelized and achieved in real time. And then in order to have a proper data augmentation and refined or optimized for this problem, instead of generating beforehand all the combination of data augmentations, we propose a new adaptive data augmentation method. So now we are dealing with the architecture. In this problem, we have a CSV with all the key points of the pose. This CSV represents a sequence of poses which is assigned, for example, the letter A. So in these kind of problems, first the dataset is generated, all the images and all the data is generated beforehand, which is a sequential and CPU bounded process. Then the data augmentation is performed, making slight changes in this data in order to have more data to train the model, which can take long time, some hours, and this usage can be boosted or multiplied by 5, 10, 81, as we are going to see in this slide. And once we have the data augmentation performed, we have the model training, which is performed on the GPU. So as you can see, this process is sequential and iterative. What we are proposing is to have a new neural network that creates the different augmentations. So we are plotting the CSVs into the sequences, but this is performed dynamically while the GPU is training with another batch. So the CSVs are represented into the images in the different cores. So we have this parallelized, then this is fit into the GPU, and in the meantime, once the GPU finishes processing the batch, the neural network that determines the data augmentation is updated in order to select the most appropriate augmentation in this epoch, and also the new batch is loaded in parallel. So this is an iterative process in which we are optimizing a neural network that defines the best data augmentation in each case, and then the data input pipeline is parallelized. So the methodology, we have here an original human pose. If we want to create dynamic data augmentation, we can move the hands in the axial axis horizontally, and we can have like another data augmented images. Then we can move only one of the hand, for example, in the vertical axis, and the other hand remain static. And then we can have like a diagonal movement of one hand and an horizontal movement. So doing all this combination, we can have up to 81 data augmented variations for each sequence. In TensorFlow, for example, when the dataset is being loaded, in most of the cases, the dataset fits in the tf.data.dataset.fromTensorSlides function. This function takes all the data and store into the RAM memory. If the data fits in the RAM memory, all is perfect. But in this case, since we are having a lot of data, this is not possible. So we can see that we have two arrays, the data, which is the n represent the batch size, 12 is the number of images of a sequence, and 100 is the size of the image, and the 3 is the number of channels of the image, and then the label is the gesture. This function may define the batching, shuffling, and the parallel load, so this is optimized for the TensorFlow, but as we said, we can have some memory errors. So what we performed is a sequential input pipeline in which a new sequence is required to be loaded. So all the images in the sequence are generated and loaded. Then this is performed outside the TF graph, since we are using functions which are not graphs in TensorFlow, but use NumPy or similar libraries. Then the following data is loaded, and then the next item. Once we have, for example, here the batch size is 3, the batch is generated and the model is trained. So we have, in this case, as you can see, a sequential input pipeline in which we are loading sequence by sequence until creating the batch. And once this is performed, the GPU trains. What we have performed in parallel is dynamically load the different items of the batch. So one core is processing one sequence. Once we have the 3 sequences, the model is trained. So the load of the sequences are performed on parallel. This is performed using the Python multiprocessing module in a very straightforward way, which defines a map, and the thread function is executed in a map that distributes the data into the different available cores. And this schema is flexible and modular. Another question, since we are creating the data dynamically, when the GPU asks for new data, we ask which set of augmentation is better for the training, because we are generating 81 variations for each sequence, but which of them make the model improve. So if we perform the data augmentation beforehand, we can reach the disk limit. The data augmentation is not optimized for the problem, and we should execute again with new augmentation policies. For example, if we consider another variation or data augmentation policy, the dataset may be regenerated again. So our solution is a new neural network which decides which augmentations are executed at each epoch. The objective of this neural network, which is a multi-layer perceptron, is to maximize the accuracy of the sign language recognition model while minimizing the number of augmentations. We want the best model with the least number of data. In this case, it selects the most adequate augmentation that generalizes the model. Well, this approach can be seen. We have the neural network, which generates some data augmented sequences. The model is trained. We have here like a 90% of accuracy and 90% of augmentations. Now the neural network is updated. This neural network generates some new data, which in this case is more augmentations, and the accuracy is increased. So the model updates the same neural network, and in this case the neural network generates 85% of augmentation, but the accuracy is increased. So as can be seen here, the neural network is generating less, but accuracy is also increased. So the neural network may, in the following steps, reduce the number of augmentations if the accuracy is still improving. As for the results, we are training this approach in a HPC cluster, which has a NVIDIA Tesla 830 GPU. Also, we are using a 32-core processor by AMD. The use case is a neural network that is composed by a convolutional neural network and a long short-term memory network. The baseline data augmentation is to generate 81 variations for each sequence, for each data. And in this case, the dataset lasts 132 minutes to be generated. In this case, a total of 4 users are incorporated, following the leave one subject out validation, and having 110 sequences per user. Here you can see the graphic that shows the acceleration of the proposed input pipeline. As you can see in yellow, we have the data set, the time that is taken to process 50 sequences of data in sequential. And in orange, we can see the same, but using the parallel approach. as you can see, when having a larger batch size, in this case 24, the speed up is 3.71 with respect to the sequential version. So as the batch size is larger and the number of cores that are used is larger, the acceleration is higher in this case. Here we can see the variation of the number of cores that are used in the parallel approach. In pink, red, orange, and yellow, we can see the different batch sizes that are used in the experiment. And then in 3 cases, we can see that the 16 number of cores is the most adequate number of cores that are used to parallelize the function. However, when having a batch size of 1, the best number of cores is using 80. Well, now, in order to compare the data augmentation policies, in the left part we can see the problem without the adaptive data augmentations, but having 81 variation for each sequence of data. We can find here that the best epoch is the epoch number 5, reaching 100% of validation accuracy. The training time is 2681 seconds, while using the adaptive data augmentation and restricting to 15 variations for each data, we can see that the best epoch is at 30, but the training time is less, is 1219 seconds. Here we can see the policy, the reduction of the data augmentation that can be seen in the policy network, which is the neural network that decides the data augmentations. And at the epoch 30, the reduction of the data augmented samples is about 40%. So in conclusions, in this work, a customized input pipeline for the problem of sign language recognition using human post-estimation is proposed. It avoids memory errors and offloads preprocessing and data augmentation to the CPU in real time. A parallelization strategy based on multiprocessing library of Python has been proposed. It speeds up the input pipeline, reaching 3.71 with respect to the sequential version. The pipeline supports adaptive augmentation policies using a neural network, enabling transformation parameters to evolve during training based on model feedback. Empirical results demonstrate that the effectiveness of the approach in reducing training time, while also avoiding stored augmented data in disk. In future works, alternative parallelization strategies based on threading from Python and MPI pthreads of C will be explored to further parallelize the input pipeline processing. Furthermore, the approach will be tested with other deep learning frameworks, such as PyTorch or JAX, to evaluate the generalizability and adaptability of the proposed pipeline across different ecosystems. Thank you very much for your attention.